In this lecture, we're going to make that jump from univariate statistics that we've been talking about so far to bivariate statistics. We have two variables that we're dealing with at the same time. We're going to talk about how to predict one variable, essentially we call the independent variable, based on a variable, we're going to predict the dependent variable based on some measured, easily measured independent variable. So the dependent variable is, say, y is going to be dependent on the variable x, which is our independent variable. So we have two variables, independent and dependent. So again, univariate, bivariate. All right, this figure gives us some indication of the type of problem that we're trying to solve. So in this case, we have the weight of, these could be people, it could be some, say, a tree of some age, and relating it to its height. So the question for linear regression, or that we're going to be dealing with, is can we predict the height based on some independent measurement of the weight in pounds? This is called a scatter plot. So each one of these is a measurement. So if I took a measurement here, let's see, there we go. It's essentially 18 pounds, and the height is about a little bit more than, say, 20 inches. Okay, so each one of these is a measurement. And well, we're going to work on how we make that jump from these independent measurements to having a way of predicting based on, say, future measurements of weight. How would we measure the height? Predict the height to be. All right, so we've been talking about this scatter plot. So here's another scatter plot where we've actually drawn a line through this data in a way that probably feels intuitively okay, that it's going to be a relatively good predictor of my dependent variable based on my independent variable. In other words, if I picked a value here for my independent variables, went up to 20, I might predict that my dependent variable would have a value of about, say, 7.5 or 8. So we call that linear regression, which is essentially the process of finding the best, I'll put that best in quotes, line fit through multivariate data, usually, in this case, bivariate data. So the kind of problem we're dealing with is essentially to generate a line so that the deviations from the line are small. So when I talk about deviations, imagine these blue dots here. Well, let me start from explaining what this graph is. This is the study time in hours. So you have different students, and here's the grade they get in points. So these study time varies from 0 to 7 hours. The grades vary from 0 up to 80. And as you might expect, the more time they study, the greater the number of points. So I might want to make a case, well, you should be studying more. And I'll do that basically using this data set. This could be 1, 2, 3, 4, 5 students. Okay, so the deviations that I'm talking about are the deviations of the actual measured value minus the value on the line with the same independent variable. So let me get a little bit more specific. So let's say we have study time 2 hours, and the actual for this particular student was about 51 points grade, and the predicted value is right here about around 40 points. Okay, so the deviation in this case would be 11. So you can imagine if you could draw a line that actually passes through all these points, well, that would be an accomplishment. But that would mean essentially that your predictor is essentially predicting perfectly for all of your measurement points. So that would be quite an accomplishment. But in most cases, that's not going to be the case. There's going to be some unexplained variance, which is essentially these deviations from the line. Okay, and you want those deviations to get as small as possible.